In our previous video, we discussed the concept of a permutation. If you haven't already watched that video, I would encourage you before viewing this one to go back and view that. In this video, we're going to discuss the concept of a combination. So the first thing I want to do is draw your attention to a compare and contrast of the two topics. A combination, in contrast to a permutation, is an instance when we're considering a collection of objects when the order is not important. What would be an example of that? Let's say that you are ordering a two-topping pizza. We would all agree that when you're ordering a two-topping pizza, a pepperoni and sausage pizza is the same thing as a sausage and a pepperoni pizza. Reversing the order of those two things doesn't matter in this case. That's in contrast to problems with a permutation where the order does matter. Let's take a look at another example. Let's say that you have a pool of 5 people and you're determining how many different ways can you choose 3 winners from that pool of 5 people. Well, if the prize is the same to all 3 people, then choosing 3 people one way and those same 3 people a different way doesn't really change the outcome, so the order doesn't matter. Now, as you're going to see here in an example problem, slight tweaks to the wording of the problem can affect whether you're dealing with a combination or you're dealing with a permutation. But big picture-wise, a combination, we're dealing with combinations when we're looking at a collection of objects where order does not matter. Similar to permutations, combinations have a notation. You'll recognize this if you watch the video on permutations, but for combinations, it's the exact same notation, only instead of a P here in the middle, we have a C. So NCR. The way we read that is N objects chosen R at a time. In terms of the actual definition of what a combination is, NCR is equal to N factorial divided by N minus R factorial. And you'll notice at that point, that's the exact definition of a permutation. But then we have one extra term multiplied by R factorial. Let's take a look at an example problem that actually involves both a combination and a permutation. And you see if you can pick out and follow along with me on which of these problems is dealing with a permutation and which is dealing with a combination. Here's the example. A school club has 10 members in it. And we want to know, A, how many ways can 3 members be chosen from the 10 members to form a rules committee? That's part A. Part B, we want to know how many ways can 3 members be chosen as president, vice president, and secretary. Now I want you to answer in your own mind, based on what we've discussed, which of those two is a combination and which of those is a permutation. Hopefully you come to the conclusion that down here in part B, because the 3 roles are different, president, vice president, and secretary, the order matters. The order matters. If you have the same 3 people where person A is president, person B is vice president, and person C is secretary, if you reverse the order of these, then they are in different roles, so the order matters. So in part B, we're going to be dealing with a permutation. We're going to use a permutation calculation to solve that problem. In part A of the problem, you'll notice that the rules committee is general, meaning that it's just a committee without specific roles. So having person A, B, C in the committee would actually be the exact same thing as having person C, B, A. That is the exact same committee. It's the exact 3 people, since we're not differentiating between what they will do. So in this case, we would say order does not matter, and so we are making use of a combination. Now, in both of these calculations, we need to actually come to a numerical answer. So for part A, we have 10 members that are being chosen 3 at a time using a combination. If you calculate that out, using the definition of a combination, you come up with 120. In part B, we have the same exact thing, 10 chosen 3 at a time, only instead of concerning ourselves with a combination, we're now using a permutation. So we have 10p3, and the answer is 720. Now, hopefully it makes sense to your intuition that everything else being equal, so notice the 10 and the 3 are the same in both of these, permutation is going to have a lot larger answer. Let's discuss and think about why that is. When order matters, then A, B, C is a different result than C, B, A. When order does not matter, A, B, C is the same result as C, B, A. So it would make sense then that, generally speaking, when you're dealing with the same number of objects chosen the same number at a time, permutations are always going to be significantly larger than calculations. In our third and final video on this section, we're going to do a couple more example problems that are a little bit more advanced and require you to have a little bit deeper knowledge of permutations and combinations.